Uh, okay, so today's class will be doing the remaining part of discussion of the heterocyclic chemistry. So without further delay, let us quickly start. So the discussion will be mostly on the fused system. Here you can see the structure is the benzene fused with one heterocycle that is 5-membered ring. Okay, the X represents different element. Now, among these particular structures, we have particularly indole, benzofuran, and benzothiophene. Okay, so what we'll do is we'll discuss mostly the indole, and benzofuran and benzothiophene. I'll provide the related study materials. Okay, it will not be too much, but the indole will be just doing the all reactions. Okay, so if we look into the indole, it is just the again one aromatic heterocyclic compounds where you have the 6-membered benzene ring fused with the 5-membered pyrrole ring. So you have the general structure. I think all of you know. So this is the benzene and this is the pyrrole. They are being fused. Now this compound we get as liquid, so it is liquid in state at room temperature. You have boiling point of around 253 to 254 degrees centigrade. Now what is important is that generally we find this compound as in in many naturally occurring products as the base heterocycles. Okay, and many drugs has been developed based on that. Now one thing we often see in the exam, that the comparison of the basicity. So if you look at the indole and pyrrole and pyridine, quickly can you tell which one will be the most basic and what will be the order? If anybody want to give the answer quickly. Among these three, which will be the most basic and which is and what will be the order of basicity? Can anybody get the idea? Any idea you have? Okay, so let me tell you. If you look at the pKa, okay, of these compounds, that means what is pKa? You have the protonated form of the corresponding compound. Okay, the pKa of the protonated form of the corresponding compound. So for pyridine, you have already come across that the value will be 5.2 nearby. The pyrrole is around, I mean, -4 nearby, and indole is around -2.4. Okay, now from here it is clear that this is the most basic. Okay, so you have, this is 1, if I put this is 2 and this is 3, so the order is going to be 1 is the most basic, then you have 3, then you have 2. Okay, now a quick reasoning you can put as the lone pair, the basicity is based on how it is donating its lone pair. So the lone pair for pyridine can be donated to H plus, though it is poorly basic, not as basic as its saturated form. So after doing that, you have the structure like this, right? You have NH, this is plus. Now this compound is protonate form is still stable. It is aromatic in nature, though the lone pair is at sp2 hybrid orbital, so it cannot be donated easily. That's why your basicity is less. But the compound wise, after forming the H plus, I mean the protonated form, it will be still quite stable. Now, when you go for this one, generally, if you talk about the basicity, we want to add the proton to the donating atom, right? So you'll have the protonation at the nitrogen. Okay. Here also you'll be expecting the same protonation at the nitrogen when you talk about the basicity. So you have protonation here, right? But these two cases, what you see is that when it will be protonated, the compound will be very, very unstable, right? Because you have the protonation here, and now you have a closed system having 4 pi electrons, right? And you have a positive charge, kind of anti-aromatic structure, okay? And you have the same here. Okay? That means it is losing its property of aromaticity. So that's why the corresponding compounds are not stable. Okay, so the protonation at nitrogen is not stable. That's why you see the value is very, very less, -4. -4 means it is very less. It can easily be dissociated. So the proton can easily come out. Okay, so it can easily form, I mean, it can easily come back to this uh, the non-protonated form. Understood? That's why you have it is very less value. Now, between these two, indole and pyrrole, what you see is that indole is a bit stable because you have the benzene ring, which at least getting preserved its aromatic character. Okay, whereas for pyrrole, it is completely losing its aromatic character. Okay, if your protonation is happening here, it is completely losing its aromatic character. But for indole, the benzene ring is being intact. Only the pyrrole ring is getting disturbed. Okay, so that's why this is a bit stable than you have the situation for pyrrole. So this is, you have to note down. We see these questions many times in exams. Okay, let us move forward. Then we have the synthesis. One of the most important syntheses is the Fischer synthesis. Okay, now in Fischer synthesis, this is, if you look at here, the benzene ring is there, and now you are having the construction of pyrrole. Okay, the pyrrole ring formation here is happening here. What is the source here? You are using the hydrogen type of compound. So N substituted hydrogen. Okay, medium, you're using acidic medium, either Bronsted acid or Lewis acid you're using. Now what you have to do is, if you look at here, you have 2 nitrogen. Definitely in the product you have 1 nitrogen, so 1 nitrogen should come out. Okay, now the structurally, if you consider, so this is the 3 system, this is the excess one, you can think. Okay, now 3 is there, you need just 2 more. Okay, so for 2 you need 1 2 environment, 2 carbon system where you have alpha hydrogen. Okay, now this is, we can write as 3 plus 2 approach. Getting? Now you have ketonic substrate, so NH2 can easily quickly make the imine. Okay, so this is the imine formation, and then this one is undergoing enolize, I mean the tautomerization. So you have tautomerization here, proton transfer, you have hydrogens, right? So here you will have a proton transfer reaction. So this is proton transfer is happening, and then you have you have to add H plus or the Lewis acid. So what you will see is that the N will be protonated, and then that will drive the reaction, the cyclization or the CC bond formation. Okay, because this is protonated, so it will try to break this bond. Will be it will try to break this bond, and that's why you have the driving of the reaction. So uh, this is the movement. So when you put the heat, what will happen? You have now the environment of uh, 1, 2, 3, and 1, 2, 3. So you have gone through the kind of 3 plus 3 sigma topic rearrangement, cope rearrangement. You have learned, and you have learned also Claisen rearrangement, right? So there you have seen the oxygen was there in Claisen rearrangement, but you have 3 sigma tropic rearrangement. So here that is the case. You have the same environment. So if you heat it, you have the CC bond formation, and this is breaking. Now after that, since the benzene ring is getting losing its aromaticity, so it will try to regain it. So that's why if you see, this proton will be lost and you will have the NH2. So this is NH2. Now this NH2 is free. This side by NH2 is still protonated. So that means this is having del plus. So nitrogen will prefer to attack the carbon, and you have 5-membered ring construction. And after that, you have elimination of NH3. Okay, and this double bond formation. So it is happening via 3 plus 3 sigma topic rearrangement. Okay, so this reaction is very important, Fischer synthesis. Then what we see is that another important synthesis is Bissler synthesis. Bissler synthesis is quite easier. Here you have the substrate itself is disubstituted amine. Okay, now here you have one electron withdrawing group, okay, which you can easily get rid of if you treat with base, and you have another group which is again the ketonic group. Okay, now this one, if you treat with the phosphoric acid or the acidic medium, you have again the similar kind of reaction. You have CC bond formation, if you look at here, and then you have dehydration. Okay, and since if you look at here the KOH aqueous, so we just need to boil it. So what will happen? The OH minus, this will help dehydration, as well as this will attack here, and finally this will get rid of. So you have N minus, and N minus will take the proton from water, so it will be NH. Okay, so this is we know as the Bissler synthesis. Now this is the keto. You can use the aldehyde form also, but since the aliphatic aldehyde, this part, if you look at the aliphatic part, right? If you use the aliphatic aldehyde, uh, generally aliphatic aldehydes are very less stable. So what is better to use is its protected form, and protected form of aldehyde is the acetal. Okay, and that is here. So if you look at this, is we can think as your parent compound is this one. You have nitrogen, okay, and then you have CHO. So this is your aldehyde. Okay, now this aldehyde is unstable because this part is aliphatic part. Okay, so aliphatic aldehyde are very unstable, very difficult to stabilize. So what people can do is they can stabilize by making acetal. So that's why the acetal is can be utilized. And again, the similar type, you just do use the strong acid, it will be cyclizing. Okay, so you have protonation here, then you have the ring formation. Okay, so this will come out after protonation. Okay, and finally you have proton here, so that also help you to gain the aromaticity. Okay, so you'll have this structure, this mechanism you will try. Now here, if you see, you have the acidic medium, you have anhydride is utilized, so that's why it is preserving. Okay, now to get rid of this one, what you need to do, you just need to heat it with aqueous KOH. Okay, and you will be ended up with the indole. Okay, So N unprotected indole. So you have free of this one. Got it? So this is the way we do the synthesis of indole in distillate synthesis. Now you have another synthesis is Lim-Rubal Bacho indole synthesis. So this one is again you have a substrate where you have a nitro, so orthonitro-toluene type of substrate derivative. Now since you have nitro here, that means this proton become acidic. Okay, acidic. So if you use the strong base, this proton can easily be abstracted at the benzylic position and then it can get stabilized. So what you can think is you have, if you use the base, so the base will abstract these protons, you have this minus. Okay, and you have nitro already. Okay, so this can be stabilized. Okay, so that is the thing here. Now what is happening, you have DMF, so this carbon can react with DMF. So DMF is NN dimethyl formamide. Okay, NN dimethyl formamide. So you have acidic, you have this formyl group, so that can do condensation reaction. Okay, so that's why you have CH. Here you have at least 2 proton. Okay, so 3 protons are there, so you can have 2 proton involvement and this oxygen. So water can come out, kind of aldol type of reaction. Okay, and you have formation of this CC double bond. Now what is your job? Then your job is to make the CN bond formation, because you have already 1, 2, 3, 4, 5. Okay, so just you need to CN bond formation. Nitro is not nucleophilic, so what you have to do, you have to do reduction. Okay, so the next step is do reduction, selective reduction to make the amine. Okay, and then you have an Me2. So if you do that one, you can use the metal with acid, that type of reaction. Zinc, you can use zinc HCl or iron HCl. Excess if you use, you can do the reduction of nitro without doing the reduction of the CC double bond. Okay, and then what you will have is the cyclization. So it will do reaction, you have the negative charge here, then it will fall and NME2 will come out. So NME2 will come out. Okay, and you will get finally this as your product. Okay, so this is another reaction. You have one more reaction, that is Reisert indole synthesis. That one is again quite similar, just we are changing DMF to another substrate, that is diethyl. You have, sorry, this is the your ester OET. So you have oxalate. Okay, now this one, if you use base, definitely it will first react here and one of the weight will come out. So the connection will be like this. You have carbon, you have C double bond O COET, so that is there. Now you do the reduction, so nitro will be reduced to amine, again selective reduction, and then what the amine will do, you have the CC double bond and CO double bond, so it will quickly make the amine. So what will happen, and then let me write the formation of, so this is going to form, okay. Now this will be, you have protons here, so what is going to happen, it will be aromatized. Okay, it will get this product. So this is the reaction. These two reactions are quite similar, just you have the substrate different a bit. Now you have one of the most important reactions, the Fukuyama indole synthesis. Now this one I'll give as home task. So who can write the reaction mechanism? I'm not giving the condition. If you look at this important condition, okay, what will be the reaction mechanism to get this product? Okay, so this will be your home task. Okay, home task. Now we'll move to the reactivity. Electrophilic reaction. You have, if you look at the structure, you have indole here. Now, if you directly add the electrophile, what will happen? The reactivity will be at the beta center. So this is 1, 2, 3. So 3 center or the alpha beta center. Okay. What will happen? Your reactivity will be like this. So your electrophile will be added to the beta position. But if you use in a different way, if you protect the N, okay, and then do the lithiation, your reaction will be at the alpha position. So here if you look at, suppose you have used a strong base to abstract the NH proton, okay, N minus, now this N minus, you'll do the protection first, okay, some anhydride or acyl chloride kind of thing if you use, so it will be protected, and then this is your protection. Then if you do lithiation, so lithiation will occur at this center. Okay, lithiation will be occurring at the center, so it will abstract the proton. So suppose you are using butyl lithium, what will happen? Butyl lithium will be abstracting proton from here. You have lithiation. Then if you use the electrophile will be added at the center. Okay, so this is the way we do selective electrophilic reaction at the alpha and beta position. Nitration, generally if you think about nitration, quickly our mind gets stuck with the mixed acid reaction condition, means acidic presence of the reaction medium. So what we will see if you have the acid presence in case of indole. Okay, now this is the indole. If you use the acid, what people have confirmed that if you have the acid presence at room temperature, what will happen? It undergoes kind of dimerization. So first is that you have protonation. Okay, protonation. So indole prefers to be protonated at this beta position rather N protonation. Okay, so that happens here. Now after that, what will happen? You have another indole. So that indole, so what it will do? It will attack this position, and you have this neutralization. Okay, and then you will have elimination of proton and regaining of aromatization of the indole structure. Okay, one of the structure here. So you will get this dimerization. Okay, that's why it is better to avoid the acidic reaction medium, acidic condition. So acid-free nitrating agent, one of them is benzoyl nitrate. Okay, benzoyl nitrate. So you have pH, C double bond O, O, N. Okay, so this is the benzoyl nitrate. So this is used at 0 degree temperature. You have the reactivity at this beta position. So beta position nitration. Even if you protect, if you have this group at alpha position, still you don't have any problem. You have nitration at beta position. Okay, reaction mechanism is not difficult. It's directly attacking to the nitrogen center, and this is coming out. Okay, so this is easier. Now you have the N protection helps nitration at 3 position at very low temperature. Okay, now if you still use the acid, if you want to use the acid, you can have nitration at 3 position. At that situation, you have to use the low temperature and one anhydride. Okay, actually in this case the anhydride is becoming the corresponding nitrating reagent. Okay, so you will have this formation, and this will actually act as nitrating reagent. Okay, so that will help do the nitration at the beta position. Here also the similar thing. If you look at the temperature, very low temperature, and you have nitration at the beta position. So this is also known. uh, Two position protection helps nitration at 5 position. Now if you have, in this case, if you look at methyl here, and you are using the mixed acid, nitric acid and sulfuric acid, 0 degree temperature, what people observe that the nitration is not happening at the beta position, rather it is happening at the 5 position. Okay, at this 5 position. Why it is so? Uh, the first thing is that the sulfuric acid, it does the addition reaction with the pyrrole. I mean this indole pyrulic CC double bond. Okay, so if you see, look at, you have OSO3H and you have one hydrogen added. So kind of addition reaction. Okay, now when you have addition reaction, this has lost its aromaticity, this part. Now the nitrogen is just acting as kind of secondary amine. Okay, now if it is secondary amine, you know it will be activating at the para position for the reaction. Okay, and that is happening, the nitration is happening at the para position, and after that the elimination is happening, the sulfuric acid is coming out. Okay, and you have nitration at this position. So this is your nitration reaction all about. Now sulfonation, you should use the so sulfonation reaction we are discussing. Now here you have non-protonated system. Okay, so you have pyridine system here, what you can use. Now the similar way the reaction will happen. You have sulfonation, so SO3 minus is incorporated. Now you can just use the acidic medium to do the protonation. Okay, that is the way to get good sulfonated compounds. Halogenation, you just use the bromine and pyridine system at 0 degree. You can have the 3 position bromination. Iodine, for iodine, you just need to use the basic condition. So KOH you have to use iodine, and you'll get the iodination here. So DMF as the solvent. Okay, the reactions are as usual. You just have the kind of this attack. Okay, you have I. So you have this is the situation. Here bromine will also have the similar situation. Only the changes are here the KOH has been used as base. Here pyridine has been used as base. Those are the tiny changes, but the reactions are similar, of similar mechanism. Now you have acylation. Now this is a bit important. When the indole is treated with acetic anhydride in the presence of acetic acid and heated, what we found is that the formation of this this compound, where you have two acylation, you have C acylation, you have N acylation. Okay, now in a separate experiment, when the N acylation is done in a selective way by abstracting this proton, making N as negative, and then reacting with the acetic anhydride, so N acylation will be happening under 1:1 condition. Okay, and after that, if you do the acylation with the acetic acid and acetic anhydride, you will not be ended up with this one. Okay, so the reaction doesn't occur actually in this case. Now, from this experiment, we can tell that the progress of this reaction from indole to this particular diacylated compound happens not via N-acylation at the beginning. Okay, the first C-acylation is happening, then N-acylation is happening. Okay, it's just the reverse. You cannot actually avoid N-acylation. Always the N-acylation will be there. Now, to get rid of that one, you just need to treat with concentrated hydroxide solution, okay, under a heating condition, and you can break this one. So that you have seen in the last few slides. So this is attack, and finally this is, it will be open, and the protonation will be happening from aqueous presence. Okay, so the presence of water will be providing the proton for the N protonation. Okay, so this is the acylation reaction. Now, one of the important reaction is the formylation, and formylation reaction is generally done by Vills-Meyer-Hack reaction. Very important reaction. You go through the mechanism a bit different way. The mechanism it occurs. The generation of Vills-Meyer-Hack intermediate, that is very well known. It will form, and then you have the CC bond formation. So this will happen after that, the deprotonation. So it will be generating this one. Now this one, what it will do is it will produce the dehalogenated this intermediate, and this intermediate, what it will happen further, if you treat with the base, you have deprotonation here at the N center. Okay, now the hydroxide under heating condition, it can react at the center, so you will have this movement, and water will be taking water will be providing the proton, so you will have this particular compound. Now after that, you have the production of aldehyde group. How it is happening? You have this elimination. You remember, I always tell, if you have a carbon having hydroxy and another living group, okay, generally it will generate the CC CO double bond. So this is the happening. So you have NMe2 and OH, so this will produce the CO double bond. So that is, you have the aldehyde here. Okay, so this is the mechanism. Alkylation is not too much important, but still, if you use the excess methyl iodide, what will happen? Methylation will happening step by step. So first methylation will be at the beta position. Okay, then you have a regaining of aromatization. You'll have this one. Then again you have the beta position. Okay, methylation. If you have excess methyl, so this will come out. You have the dimethylation here. After that, what will happen? The migration of methyl to the alpha center. So that is happening. You have a positive charge here. You have proton, so it will come back to its aromatic form again here. After that, in six successive way, you have further methylation at the nitrogen center, deprotonation. Then again, you have methylation to the 3 center. Okay, so ultimately you will have 4 methyl, where you have the 3 or the beta position will have dimethyl. Okay, so 1, 2, 3, 3 tetramethyl 3H indoleum iodide. So that will form if you use the excess methyl iodide. Generally, the controlling of this reaction is difficult with one equivalent of methyl iodide. A Manishi reaction, that is the addition of CH2NMe2. Okay, and at low temperature, it is found that the Manishi reaction is happening at the nitrogen center. Okay, but if you heat it, what we see is that the movement of this group occurs at this center. Okay, and you can think in this way, it is happening. Okay, kind of rearrangement type of situation. Okay, that is happening, and this compound is a bit well-known compound we know as gramine. It is the precursor for synthesis of amino acid, tryptophan. Okay, so this is the gramine, and this gramine, if you treat with this particular substrate, what we see is that here you have the generation of addition of this one. So what you can think is this is kind of this type of reaction is happening. Okay, and this will form, which if you do hydrolysis, means if you treat with the base and water, the one of the ester will become acid, and this is beta keto system. So you'll have decarboxylation, you'll have finally one ester that will further undergo hydrolysis and become carboxylate, which will be protonated. So you have the sulfuric acid here, and finally you'll get the tryptophan as the product. A quite good yield, 80%. So this is one of the synthetic route of tryptophan from gramine. Now reaction with aldehyde and keto, this is a bit interesting reaction. You have, if you look at the acetone here, so what we'll see is that you have C double bond O. So here that can be connected. So you have nitrogen lone pair, so it will here, it will attack the acetone C double bond O, the carbonyl carbon. You have this one, protonation, so you'll have OH, then you have further aromatization. So you have proton here, they will aromatize, and then again you will have the same lone pair participation, and OH will come out. So you will have the CC double bond formation. Okay, if you use the acetone or electron donating or the electron rich ketone, okay, C double bond O. But if you use the electron deficient C double bond O, like kind of this one, you have the two electron withdrawing group here. What we see is that the hydroxy will form, there will be no formation of CC double bond. So this is the difference. Okay, it happens. The thing is that the elimination of hydroxy group, okay, or generation of CC double bond, it requires this center, the del positive stability. Okay, but here the del positive stability is not there because you have two withdrawing group, but here 2 methyl, so you have the del positive stability. That's why you have the CC double bond formation, elimination, or dehydration steps occur. Here the dehydration step doesn't occur. Okay, and if you use the formaldehyde, what will happen? The similar reaction, you have the formaldehyde will be reacting, and you have the CH2OH incorporation, and that can further react with another molecule. Okay, so you have elimination of this hydroxy group, you have this formation, and another indole can react. Okay, another indole can react. So you have sorry, you have this one. So you have this connection. Okay, and ultimately the dimerization, kind of dimerization, you have the CH2 group will be there in between. Okay, so this is the reaction with formaldehyde. Now nucleophilic reagents, here too much reaction is not there. You have very selective reaction, direct CH metallation. So you have the indole. If you use the butyl lithium, you have N abstraction proton, so that will react carbon dioxide and CO, so that this carboxylation will be here, which is stabilized. You have that will help the further lithiation at the alpha position, and then if you use any kind of electrophile, so that will react. So if you use this one, the halogenation, if you use other group, you can incorporate that group. Okay, sulfonation, if you do protection the N and then treat with the butyl lithium, you have again the similar way, the alpha position will be lithiated, and that will react with carbonyl compound, and you have hydroxy, I mean you have alcohol generation. Okay, and then you can deprotect this nitrogen. Okay, so this is the reaction, metal halogen exchange. So if you have halide in the system, in the indole, if you use the butyl lithium type of reagent, what will happen? This will attack here. You have negative charge generation. Lithiation will be here, and then that can act as a nucleophile. So if you use any kind of electrophile, that will react. So you have this is so what will happen? This carbon will attack this center and you have this one. So this is the incorporation. Similarly, if you use stanic system, trimethyl tin chloride, what will happen? It will attack the tin and you have incorporation of tin. Okay, and another reaction, similar way, if you have the halogenation at the benzene ring, halogen at the benzene ring, that can also do the same type of reaction. Butylation, I mean the butyl lithium you use, you have lithiation, and then you can incorporate a particular group formylation. Now DMF here used as the formylating reagent because you have this is your NMe2. So the lithiation, the carbon can now attack here and NMe2 will come out. So you have CHO group incorporation. So these are the all reactions based on indole. So the remaining of benzofuran and thiofuran that I'll give as study material just to go through. And we'll discuss the azoles and other in the next class. Okay, so maybe tomorrow that we'll discuss, and photochemistry will start in the next coming weeks. Okay, so you just go through. It is a bit rapid way. I told you just go through, try to get your understanding clear. If you have any queries, you ask always in between, or anytime you just WhatsApp me, or you can call me or anything. So I'll come back to you and give your answer. Okay, so thank you for your attendance. Thanks.
Sir.
Just go through
Thank
all
you,
those
sir.
things. Okay. Yeah.
Thank you, sir.